ladies and gentlemen. Let me start the presentation on pounding between buildings and bridge segments during earthquakes. Well, it has been observed during earthquakes that adjacent buildings might come into contact even several times during the time of the excitation, if the separation distance between them is not sufficient so as to accommodate the relative movements. And in case of buildings, the major reason which may result in such collisions is due to the fact that they might have different dynamic properties, and that will induce the so-called out-of-phase vibrations. And in earthquake engineering, these repeatedly observed collisions are often referred as the earthquake-induced structural pounding. Similar situation might also concern longer bridge structures. However, in this case, the reason which might result in collisions between adjacent superstructure segments is usually related with so-called special seismic effects related to the propagation of seismic wave. Well, this is due to the fact that when the wave travels along the bridge, then there are different inputs on adjacent piers, and because of that, adjacent superstructure segments are excited in different way, which may finally result in collisions. Different types of damages were observed as a result of structural pounding, starting with some local damages at the points of contact, as it can be seen on this transparency. Also, some more severe damages can be observed at the locations where contact takes place. And in some cases, we can also have a total collision of colliding building, as it can be observed at this transparency. Similar situation might also concern bridges. On the left side of this transparency, we can see some local damage to the points of contact between the superstructure segments. And in some cases, pounding was identified as one of the reasons for falling down of the whole superstructure segments. Well, different types of structural models as well as models of structural poundings is often used to model the phenomenon. The most simple one is to simulate the structure as single degree of freedom system, as it can be seen on the left side of this slide. That simulation might concern, for example, single-story buildings, or also in some cases, superstructure segments of longer bridges. On the other hand, in case of multi-story building, we can create multi-degree of freedom systems, also with the mass which is lumped at the floor level. And in most of the cases in such kind of models, we use impact elements in the form of some kind of springs or dampers or spring damper elements. And also different types of pounding force models were used. So different types of those springs and dampers were applied. A very simple one is the linear viscoelastic model, which is expressed by this formula. In order to model the relation between the force and deformation, the nonlinear elastic model following the Hertz law of contact is often used. However, the drawback of this model is that it does not account for the energy dissipation during contact, because this is purely elastic model. In order to overcome this disadvantage, the nonlinear viscoelastic model was also proposed, and this model is combined by two different equations, different for the approach period and different for the restitution period. In all of those models, the key parameter is the coefficient of the restitution, denoted here as E. When E is equal to 1, it means that we deal with perfectly elastic impact. In the case when E is equal to 0, it means that we have perfectly plastic impact. Well, some kind of experimental verification of the accuracy of different pounding force model was conducted using the shaking table experiments, as it can be observed on those two photographs. The experiment was conducted for different building materials, so we can study concrete to concrete pounding, steel to steel pounding, and timber to timber pounding as typical materials used in construction. The mass of all the structures were exactly the same, apart from the fact which material was used. So you can see that some additional plates were also added, for example, here and also here, so as to be sure that the mass is identical for concrete, for timber, as well as for steel structure. The dynamic equation of motion for pounding equals linear response was used so as to make some numerical analysis in order to verify the accuracy of different pounding force models. And this equation is expressed in this transparency. The key parameter here is parameter delta, which allows us to check whether we deal with collision or not. So delta is equal to x1 minus x2 minus d, where d is the initial separation gap. If delta is smaller or equal to 0, that means that we do not have any contact, and then pounding force is equal to 0. In the case when delta is larger than 0, contact occurs, and appropriate value of pounding force is calculated for different pounding force models. The difference between the results of experiments and the results of numerical analysis can be assessed by calculating the normalized root mean square error so as to verify the accuracy. And here we can observe some examples of the results. These results are for the concrete to concrete pounding. On the left top, we can see the result of the experiment. And then we have the displacement time histories for different models, linear viscoelastic, nonlinear elastic, and finally for nonlinear viscoelastic model. These time histories are for the El Centro earthquake. Similar results were also observed for steel-to-steel pounding, so I will move to the next slide and make some comments. As it can be seen, the simulation errors are more or less similar for different earthquakes, for different pounding force models. The smallest value was always observed for the nonlinear viscoelastic model, a little bit larger for the linear viscoelastic model. However, when we go to timber pounding, the situation is a little bit different. We can see on the C slide, on the C graph, which is described for the nonlinear elastic model, that the simulation error is relatively large. This is due to the fact that in the case of timber pounding, more damping is involved because the coefficient of restitution E is equal to 0.6. So in the case of collisions with larger damping, elastic model is not really recommended. Further analysis can be conducted for more sophisticated models, but still quite simplified with the lumped masses. Let us have a look, for example, at the analysis for collisions for pounding between 3-story adjacent buildings. The one on the left side is relatively flexible and light, and the one on the right side is heavier and more stiffer. This is the dynamic equation of motion, which can be used this time for the nonlinear response of such multi-degree of freedom systems. In the middle of the slide, we can see the conditions for the linear range as well as for the non-linear range. And again, the contact occurrence condition in the case when delta is smaller or equal to 0, then it means we do not have any contact. And when delta is larger than 0, then contact occurs. And here we can observe some examples of the results. The first graph shows the displacement time history for 2 colliding buildings, also for the Centro earthquake. It can be seen from this graph that in the case of the left building, which is flexible and lighter, pounding was really very catastrophic, because after the third collision, it resulted in permanent deformation of the structure. On the other hand, we do not see any major changes in the response of the right building, which is stiffer and massive. We can see on the lower graph that in this case, we could observe only 3 collisions with relatively large pounding force values involved. Let us have a look also at the relation between the peak displacement and the gap size, and those 2 graphs show the response for the left building at the top and right building at the bottom of the slide. And again, similar conclusion can be drawn, meaning that in the case of the quite flexible and lighter building, major differences in the response can be observed and major changes in the peak displacements may take place. On the other hand, in the case of the right building, so massive and quite stiff, the change in the gap and pounding does not have major effect. Well, these were quite simplified lumped mass models, but also detailed numerical analysis using the finite element method can be conducted. And this is actually the real case study of pounding between the Olive View Hospital main building and one of its independently standing stairway towers that was observed in the reality during the San Fernando earthquake of 1971. The model of both buildings can be seen on the left side of this transparency. So the stairway tower, which is quite small and again lighter, and the main building, which is relatively heavy and stiff structure. All structural members were modeled as 4-node multi-layer shell elements, and pounding was controlled by gap friction elements. On the right side of this transparency, we can see the gap friction element as one of them which was used in the analysis. In this case, different approach was used when collision was detected. 2 nodes were fixed in the longitudinal direction, and also friction was applied in the vertical and transverse direction so as to simulate a real collision. And we can observe some examples of the results of the analysis. Firstly, the displacement responses in the longitudinal direction for pounding involved, and for the case where pounding is not observed, that is the green and red color curves. And again, we can see on the left side of this transparency that in the case of pounding, substantial increase of the response can be observed as a result of those collisions. On the other hand, for the main building, only small changes are visible on the right side of this transparency. Quite similar conclusions might concern also transverse, as it can be seen on this transparency, as well as the vertical responses of the structures. So again, in the case of the lighter stairway tower, large changes in the responses was detected in the case of stiff and massive main building of the hospital. Only very small changes in the response took place. Also, when we look at the plastic strains in concrete as well as plastic strains in steel reinforcement, in the case of stairway tower, we could observe some damage at the points of contact, but only for this building. And also for the lighter stairway tower, in the case of the cracking strains in concrete and plastic strains in reinforcement, damage was much larger comparing to the case when pounding does not take place by comparing those two results, which can be seen on this transparency. On the other hand, when we look at the response of the much stiffer main building of the View Hospital, Olive View Hospital, cracking strains in concrete and plastic strains in steel reinforcement are more or less on the same level for both pounding involved as well as for the independent vibration responses. Let me now move to pounding between superstructure segments in elevated bridges. Let us start with showing some results for the real case structure, which is the bridge which was designed according to the so-called manual for machine design of highway bridges. This is the document which is used in Japan to construct structures resistant to earthquakes. The cross section of the bridge shows that the piers are relatively massive with the relatively large cross sections. So actually they are so massive that we do not have even take them into account in the response analysis. And a very simplified model can be also created for this structure by making the mass of the whole superstructure segment to be lumped on one point and supported by the sum of all the high damping rubber bearings. Here, high damping rubber bearings were used as the isolation devices for this structure. In this way, we can create relatively simple 5-degree of freedom model for adjacent superstructure segments, meaning that each mass is related to each superstructure segment, and there is the distance between them, also denoted as d. The dynamic equation of motion for this model is presented on this transparency. It is slightly different model comparing to collisions between multi-story buildings, because the stiffness and damping matrices are also diagonal matrices, as it can be seen on this transparency. And here we can observe some examples of the results. This graph shows the displacement time history of the middle superstructure segments for different gap sizes between adjacent segments. The results are also presented for the El Centro earthquake. And in the case of the relatively large seismic gap, which is in this case 11 centimeters, that is the green light, we see that, of course, relatively large response can be observed. And the smaller the gap is, the response is of course smaller, because it's of course blocked by the adjacent superstructure segments. So for the case of 1 centimeter gap, this response is much lower comparing to the larger gap size case. However, when we look at the pounding force time history, we see that in the case of relatively small seismic gap, we have a lot of collisions, as it can be observed here, but the pounding force is relatively small. On the other hand, if we deal with relatively large gap size between segments, but still not large enough to prevent pounding, still collisions take place. So we can see that there might be only 2 collisions, as in this case, but the pounding force can be relatively large. Well, let me now say a few words about the mitigation of pounding effects. And of course, it's quite obvious that the best way to prevent structural interaction, structural pounding, is to assure the relatively large separation gap between adjacent buildings or adjacent superstructure segments. However, it's not so easy in many cases. In case of buildings, there is a kind of a pressure for designers to construct as closely as possible. This is due to the fact that the price of land is relatively expensive in many places. So that is not so easy to make very large gap size in some cases. On the other hand, making relatively large gap size in case of bridges is also not so easy in many cases, because we have to remember that if this is the highway bridge, for example, so we have to carry out the heavy traffic load over the expansion joint. So there is some kind of limit of making this gap relatively large. So that's why a number of different pounding reduction techniques were proposed. Most of them deal with installing some kind of connections between adjacent buildings of adjacent superstructure segments by means of some springs or dampers, or both linear viscoelastic elements, also using some shock absorbing devices, for example. Also, there was the idea of using the so-called collision walls so as to prevent structural damage due to structural pounding at the points of contact. Let me now say a few words about the design of structures which are prone to pounding. And firstly, in order to make the damage assessment or its prediction, and also to apply any damage reduction techniques, we need to know actually how large is the pounding force during the time of the earthquake. And for this purpose, we can use the idea which is called the pounding force response spectrum. The concept of response spectrum is not new in earthquake engineering. However, this idea is somehow different comparing to some previous analysis. Pounding force response spectrum can be defined as a plot of the peak pounding force as a function of the natural period of one of the structures. If we can imagine that we have already one old structure already constructed, and we are going to build a new one close to it, so what kind of parameters we should apply, what kind of natural period the structure should have, and how much we can go to the left or to the right side, and of course how large gap size should be so as to minimize the effects of pounding. Structures are modeled by single degree of freedom systems, and this is always the case in the case of response spectrum analysis. And plots are presented for different values of damping ratio of this new structure, mass of a new structure, as well as gap size between both structures, as can be observed on this equation. There are some examples of the results showing pounding force response spectra for a central earthquake for the specified gap size of 5 centimeters for different values of mass of the new structure. As it can be, it could be expected, the larger pounding force can be expected for the structure with the larger mass. So we can see here on this transparency that the largest values can be expected for this case. The next transparency shows pounding force response spectra for the same earthquake for the specified mass and for different values of the gap size between structures. And I would like to draw your attention to the third graph here, because we can clearly see that the larger gap we apply for this structure, the larger range of natural periods of the new structures can be applied. And also, depending on the damping ratio of the structure, different approach can be conducted. Well, coming to the conclusions to my presentations concerning buildings, the earthquake-induced pounding may have really a significant influence on the response, but on the response of a more flexible and lighter building, it may amplify its response, which may finally lead to its permanent deformation on any type of damage. It may also cause some substantial damage at the points of interaction of this structure. On the other hand, pounding involved behavior of the heavier and stiffer building is usually influenced negligibly. In the case of bridges, pounding may again substantially modify the behavior of such structure. It may increase the structural response, but it may also play a positive role at the response, depending on the pattern of collisions between superstructure segments. Number of impacts for small in-between gap size is large, whereas the value of peak pounding force is somehow low. On the other hand, when we make the gap larger, the pounding force values will show only few collisions, but the value of the peak pounding force may be substantially large, which may substantially intensify structural damages in bridges. In the case of pounding force model, we can say that the non-linear viscoelastic model of pounding force can be considered as the most precise one in simulating the pounding involved response of structures which are modeled as single degree of freedom or multi-degree of freedom, but lumped mass models, lumped mass systems. However, the linear viscoelastic model gives slightly higher simulation errors. On the other hand, it is quite simple and easier to be applied. And also the experimental results show a considerable influence on the material of colliding elements on the behavior of structures during earthquakes. In the case of mitigation of pounding effects, the simplest way to prevent structural pounding is to provide sufficiently large in-between separation gap. However, if the collisions cannot be prevented, some pounding reduction techniques can be considered in order to enhance the seismic performance of structures. And it is quite important to underline that in the process of design of pounding-prone buildings, special attention should be paid to the weaker, meaning lighter structure, for which structural interactions during earthquakes can be really catastrophic. And finally, pounding force response spectrum provides very valuable information on the peak pounding force, which can be expected during the whole time of the earthquake. And therefore, it might serve as a very useful tool at the design stage of closely spaced structures on seismic regions. The appropriate selection of the dynamic properties of the new structures, so natural vibration, period mass, damping, really have a significant influence on pounding involved response. And tuning those parameters with the old structures' dynamic parameters will minimize damage due to pounding. Of course, in not all cases, it will be possible to do it. The increase in the separation gap between structures allows us to prevent damaging impacts for a wider range of the natural vibration period of the new structure. And there are some major references on the topic, which I also used in my presentations. Thank you very much for your attention.